Hello everyone, I am Braulio Di Peñalosa. In this lecture video, I am going to give a lecture presentation of the subject with section code Math 66, and the descriptive title of the subject is Numerical Analysis. Before I am going to give to you the content or the outline of this subject, first is let me ask you a question. Of course, this question is related to the descriptive title of this subject. The question goes like this: why do we have to study numerical analysis? Okay, so to answer that question, let me open my browser first. Maybe in your case you are using Google Chrome, but in my case I am using Brave web browser. Okay, let's try to, it will be the same. I already typed the question. Okay, so why study numerical analysis? So it says here, it investigates and provides accurate solutions to real-life problems from the field of science, engineering, biology, astrophysics, and finance. Okay, there's nothing more about this answer. Let's try another. Let's say, of course, that came from scienceabc.com. Let's try Quora.com. Let's right click here. Okay, let's say this one. Okay, from Proven Bud. Numerical methods or analysis does not guarantee the exactness of the solution. Okay, so please remember this word, of any algebraic or transcendental equation, but it absolutely guarantees that the solution obtained using numerical method is very close to the exact solution. Okay, so let's try to illustrate this first sentence here. So let me open my whiteboard. Let's say open board here. Okay, so please do remember, says here, but it absolutely guarantee that the solution obtained using numerical method is very close to the exact solution. So let's try to illustrate this one using this problem. Let's try a quadratic equation. Let's try quadratic equation here. Example 1, quadratic equation. Find the roots or root of the equation x squared plus 3x plus 2. Okay, so solution. Notice that in this equation you can easily guess the solution, which is -1 and -2. Okay, so this is very easy. You can factor out. You can use factoring, not factor out. Okay, so you have let's say x plus 2, x plus 1 is equal to 0. So x is equal to -2 or x is equal to -1. So the solution set is -2 and -1. So this is very easy. As you can see here, where's that one? Okay, there are many equations whose real root is not possible, but by numerical method it can be made possible. So if you compare, as you can see here, if you compare to this problem, which is in number 2, let's try example number 2. Let's try to compare it. Let's try this problem. Find the roots of, or root of x squared plus let's say 3x, no, 5x plus let's say 3 is equal to 0. Okay, so if you are going to solve it using factoring, then you will fail. So let's try using quadratic formula. So let's say a here is 1, b is 5, and c is equal to 3. So we have x, we have, I know you memorize the quadratic formula, b squared minus 4ac over 2a. So we have negative 5 plus minus square root of 5 square minus 4a, or a is 1, or c is 3. 2 times 1. So this is negative 5 plus minus we have 25 minus, this is 25 minus 12, so over 2, and this is, if you simplify this one, if you have 13 over 2. So as you can see here, the solution is a irrational number, and if you try to use a calculator, this will result to a decimal number. Okay, so that's the point of the subject. As you can see here, if you are going to find the root, then you cannot get it, but if you are using numerical analysis, then you can locate possibly the root of the equation. So in this case, in the what they call this one, in the illustration here, this is easy to, what they call this one, to compare that if it is an exact solution, then the problem is easy. But what if you are given a problem where most of the problem, the solutions are not exact? So this plays the importance of numerical analysis, and most of the problems in the real world is not an exact, you cannot get an exact solution. So it is not only limited to the algebra problem. We can extend it to linear algebra, to differential equations, partial differential equations, and so many areas in mathematics. You cannot always get an exact solution. Okay, so let's try another. It says here, what if you are given a cubic equation? I remember, if I remember it right, there is a formula for this. But how about for quartic equation, for quintic equation? If you have the degree of the variable is greater than or equal to 4, then using numerical analysis, we can find an almost approximate real root of high accuracy if you are going to use a computer to find the solution of the given equation, okay, of higher degree, maybe n is greater than or equal to 4. So let's try another. Maybe we can use we can open the Wikipedia, which I open it here. It says here, numerical analysis is the study of algorithms that use numerical approximations. Remember this one, for the problems of mathematical analysis. What I like in this page is this one. The overall goal of the field of numerical analysis is the design and analysis of techniques to give approximate but accurate solutions to hard problems. Remember this phrase, give approximate but accurate solutions. Okay, and these are some of the few applications of numerical analysis. Let me read these three applications here. First, we have advanced numerical methods are essential in making numerical weather prediction. Okay, you can predict the weather by using numerical analysis. Of course, there's a lot of programming here. For the second, computing the trajectory of a spacecraft requires the accurate numerical solution of a system of ordinary differential equations. Number 3, car companies can improve the crash safety of their vehicles by using computer simulations of car crashes. Such simulations essentially consist of solving partial differential equations numerically, and so many other what they call this one, applications. Okay, so I guess we already exhaust the answers from the internet regarding on why do we have to study numerical analysis. Maybe you can what they call this one, maybe you can search more about this. There's by the way, there's a difference between numerical methods and numerical analysis subject. Okay, anyway, let's try to focus on on this subject, numerical analysis. Okay, so let's proceed to our discussion, and I guess we are now ready to what do you call this one, to discuss show this stuff here. We're now ready to discuss the content or the outline of this subject. Okay, so this is the outline or the content of the subject. First, we are going to, in chapter 1, we are going to discuss some of the basic concepts in calculus. We are going to review some basic concepts in calculus, and we are also going to discuss some Python basics and computer arithmetic. chapter 2, we are going to discuss the solutions of equations. This is all about truth finding. Okay, there are many methods on how to find a root of the equation. Just like what I have discussed to you earlier, that in most cases you cannot find the exact solution of the given equation, especially if you have a problem or an equation where the degree of the variable x is greater than or equal to 4. Okay, so when n is equal to 2, you can have quadratic formula. When n is equal to 3, you can have cubic formula. So you can search for that. Some of the topics that we are going to discuss here is we will be talking about bisection method. We will be talking about Newton's method, second method, and so on and so forth. Okay, for chapter 2. For chapter 3, we are going to discuss about interpolation, and some of the topics are, for example, polynomial interpolation. We can also have Hermite interpolation, spline interpolation, and so on and so forth. For chapter 4, we are going to discuss about numerical quadrature and differentiation. Some topics here are, for example, we have Newton-Cotes formula, Gaussian quadrature, proper integrals, multiple integrals, and so on and so forth. And finally, in chapter 5, for approximation theory, you can what do you call this one, we will be discussing about discrete least squares, continuous least squares, and orthogonal polynomials and least squares. Okay, so that's all that we are going to discuss in this subject. Okay, so for chapter 1, we have, or section 1, first is we are going to review some of the basic concepts in calculus, because we will need this in the later part of this subject. Okay, for definition 1a, this one here, this definition is very familiar, the definition of the limit of the function. So you are given a function f, and it has a limit at x sub o written in this equation. If for any epsilon greater than 0, there exists a delta greater than 0, such that the distance between the function value and the limit L is less than epsilon, whenever this inequality holds. So this is the formal definition of the limit. Okay, for the second definition is the definition of the if the function is continuous at x sub o. So this means that this equation will hold. Okay, we are very familiar with this definition. Okay, there are three conditions here. Maybe you can recall your calculus 1 subject. And f is continuous on a set A if it is continuous at each point xo in A. So this is a very obvious definition. For 1c, this is the definition of the limit of the sequence. We know that the sequence is a function, so this is the notation. The sequence has the limit x written in this form if for any epsilon greater than 0 there exists a positive number n, such that the distance between x sub n and x is less than epsilon, whenever this inequality holds. Okay, so just recall your calculus 3. Okay, recall this theorem also in your calculus. The following are equivalent for a real valued function. F is continuous at x sub o. Then this 2 is equivalent. If f is continuous at x sub o, then if you are given a sequence converging to x sub o, then the limit of f of x sub n as n approaches to infinity is f of x sub o. You can find a proof of this problem of this theorem in real analysis. Okay, another definition, we have the definition of the derivative. This is very obvious also. You can use either this formula or this one. Okay. Okay, before we are going to discuss the next theorem, let's have this notation. C to the n, capital C to the n of a, denotes the set of all functions f such that f and its first n derivatives are continuous on a. So remember that this set here is, this notation here, C to the n of a, is the set of all functions such that f and its first n derivatives are continuous on a. Okay, remember the previous definition. If f is continuous on a, then we can write this one on f only. Okay, f is an element of C to the 0 of a, and C to the infinity of a, this notation consists of all functions that have derivatives of all orders. For example, this function sine of x and e to the x are examples of functions that have a derivatives of all orders. Okay. Okay, another theorem, we have the mean value theorem. This is the mean value theorem. If f is, what is this notation? As you can see here, continuous on a. Our a here is the set AB, the closed interval AB. Okay, so it is only a continuous function. Okay, continuous function. And f is differentiable on AB, on the open interval AB, then there exists a number C in the open interval AB such that this equation will hold. If f is continuous and f is differentiable on this interval. Continuous on the closed but differentiable on the open interval. Another theorem that we are going to use later, we have extreme value theorem. If f is a continuous function, then the function attains a minimum and maximum value over the closed interval AB. If f is differentiable on this open interval, then the extreme values occur either at the points a, b, or where the first derivative is 0. So this is what we call the extreme value theorem. Another one, what happened? I cannot see here because there's my there's a video here. If f, let's try. This is what we call intermediate value theorem. Let's try to quit this one first, and then let's exit this one. Sorry, what happened? Exit that one. Says here, if f is a continuous function and k is any number between f of a and f of b, then there exists a c in the open interval AB with f of c is equal to k. So this is a very familiar theorem You can find all this theorem in calculus 1. You can also find this in real analysis. Okay, so another one is this theorem can be found in calculus 3. We have Taylor's theorem. Please review your our topic in calculus 3 for this theorem. Okay, so before we are going to end, let's try to solve this problem. Okay, as you can see here, you are given a function h of x, which is equal to x sine of x minus x. You are going to solve these three problems. For letter A, find the fourth order Taylor polynomial about x naught, which is equal to pi over 2, and use it to approximate the function evaluated at 0.7. Next is compute the exact value for the function evaluated at 0.7 and determine the error. This is what we call the absolute error. And then letter C, use the remainder term r sub 4 of x to find an upper bound for the error that you get in example 8p. Then after that, compare the upper bound with the actual error found in part B. Okay, so let's try to solve this one. Okay, sorry. Let's try to solve this one. Let's solve letter A. Okay, before that, this one here. So we have 8 letter A. Example 8. So solution for letter A. So first, let us recall our function. Okay, we have h of x is equal to x sine x minus x. So we are going to determine p sub 4 of 0.7. Okay, first note that h of pi over 2, which is after substitution, we can use this one. Where are you? Where's my mouse? This one here. Okay, sine of pi over 2 minus pi over 2. Okay, and we know that this is equal to sine pi over 2 is 1. Okay, so sine of 90 degrees is 1, so this is 0. The answer, h of pi over 2 is 0. Okay, next we are going to remember that our problem is to find p sub 4 of x. And notice here that we are going to get the derivative up to n is equal to 4. Okay, so differentiating h, we get so h prime of x is equal to the first term is we will use product rule, so we have x derivative of sine x is cosine x plus sine x derivative of x is 1 minus derivative of the second term is 1. So simplifying, we have x cosine x plus sine x minus 1, and evaluate this first derivative when our x naught is pi over 2. Okay, so this is pi over 2 cosine of pi over 2 plus sine pi over 2 minus 1. Okay, so we know that sine pi over 2 is 1, but cosine pi over 2 is 0. Okay, so this will become 0 again. Okay, 0. 0, 1 minus 1, so 0. Okay. Now we will be getting the second derivative, h double prime of x. This is equal to okay, derivative, get the derivative of the first derivative, this one here. We have product rule, we have x derivative of cosine is negative sine x plus cosine x derivative of x is 1. Second term is derivative of sine is positive cosine, and derivative of the constant is 0. So after simplification, we get negative x sine x plus 2 cosine x. So let's evaluate this at pi over 2. So we have negative pi over 2 sine of pi over 2 plus 2 cosine pi over 2. And we know that this is 1, this is 0. So what we will get here, we have pi over negative pi over 2. Okay, so we are almost done. Okay, here cosine sine. We have 1. Okay, let's get the third derivative, h triple prime of x. We have negative x derivative of sine x is cosine x plus sine x derivative of negative x is negative 1 plus 2 derivative of cosine is negative sine x. So simplify, we have negative x cosine x minus 3. sine x. So evaluate this 1, evaluate the third derivative at pi over 2. You have negative pi over 2 cosine pi over 2 minus 3 sine pi over 2. And once again, this is 1 and this is 0. So this will become negative 3. Okay. Finally, the last one, h fourth derivative is negative x derivative of cosine negative sine x plus cosine x derivative of negative x is negative 1 minus 3 derivative of sine x is cosine x. So we have x sine x minus 4 cosine x. So h, the fourth derivative evaluated at pi over 2 is pi over 2 sine of pi over 2 minus 4 cosine pi over 2. Okay, so this will become, this is 1 and this is 0. So the answer is pi over 2. Pi over 2. Okay, so we are now ready to get the fourth order Taylor polynomial. So let's move it somewhere here. Therefore p sub 3, p sub 4 of x is equal to f of, let's try to put the formula, plus f prime of x naught, we have x minus x naught 0 1 over 1 factorial plus x naught, sorry, we have x minus x naught square to factorial plus, what happened, f to third derivative, we have x minus x naught to the power of 3 over 3 factorial plus the last one of x naught, we have x minus x naught to the 4 over 4 factorial. Okay, so let's try to plug in those values. We have f of our x naught, remember that our x naught, recall, let's try to use this one, x naught is pi over 2. So evaluate f of pi over 2, the answer is 0, as you can see above here. Where's that one? This one, 0. Okay, so this is 0. Let's try this color, let's try blue, 0 plus first derivative. What's the first derivative? Evaluated at pi over 2, we have 0 again. So 0. So this is 0. 0 times this one is 0. So plus How about the second derivative? Our second derivative is negative pi over 2 and then negative 3. So negative pi over 2 x minus pi over 2 square over 2 plus negative 3. We have x minus pi over 2 over 6 plus 3 factorial is 6. And then the last one, the fourth derivative evaluated at pi over 2 is this one. Okay, this one here, pi over 2. So we have pi over 2 times x minus pi over 2 to the 4. We have 4 factorial is 6 times 4, 12, 20, 6 times 4, 4, 4 times 3, 12 times 2, so we have 24. Okay, so this is your, what they call that, fourth order Taylor polynomial. Okay, then if we are going to evaluate f of a p sub 4 of 0.7, then we approximate h of 0.7 by p sub 4 of 0.7 after substitution. So you can substitute our x, which is 0.7. So we have here negative pi over 2 times 2, this one in the denominator we have 2, and then we have 0.7 minus pi over 2 square minus 3. We have 0.7 minus pi over 2 cube over 6, and finally we have plus pi over 2 times 20. This denominator we have 24, 0.7 minus pi over 2 raised to the power of 4. So this is equal to, you can use they call this one an online calculator. So let's hide this one first. Let's go to this most scientific calculator. Okay, let's wait for the website to load. Okay, please remember that okay, our first term is negative pi over 2, this one here. So negative pi over 2 times the quantity 0.7. 0.7 minus pi over 2, pi over 2, close, and then raised to the power of 2 over 2, okay, minus 3, and then we have x, 0.7 minus pi over 2, pi over 2, close, raised to the power of 3 over 6, and lastly we have plus pi over 2 times the quantity x, 0.7, or x is 0.7 minus pi over 2, close, raised to the power of 4 over 24, okay, so enter. We round off to 4 decimal place, 2278, negative 2278. Sorry, what is this one? Negative 0.2278. Okay, using, let's move it somewhere here, using 4 digits with rounding, using 4 digits with rounding. Okay, so that's it for example 8, letter A. Okay, for our next solution for 8b. So okay, for our second question, example 8, letter B, compute the exact value for h of 0.7 and the absolute error, this one here. So let's minimize this one, so, and then let's solve 8 letter B, this one here. Okay, the exact value is h of 0.7. So we have x, sine x minus x, so 0.7 sine of 0.7 minus 0.7, okay, and this is approximately equal to, let's use the graphing calculator here, 0.7 sine of 0.7 close minus 0.7, and our answer is negative 69.14, negative 69.14, negative 0.6914, okay, and the absolute error, is h of 0.7 minus p sub 4 of 0.7. So let's move it here. We have negative 0.6914 minus, what is the value? Let's try to see it here. Negative 0.2278. Okay, negative 0.2278, and this is equal to 6914. 6914. So we have absolute value of negative 0.69, sorry, 6914 plus 0.2278. Am I right? 2278 negative 6914. Enter. 46.0.4636 0.4636. Okay, so let's recall again. 4636. Okay, so that's for letter B. So we are now going to solve letter C. So let's wait again. Let's wait. Okay, now for the solution of example 8C, let's open our whiteboard. Okay, so letter C. Okay, so this is the solution for letter C. To find an upper bound for the error, we write h of 0.7 minus p sub 4 of 0.7, which is equal to r sub 4 0.7. Okay, where r sub 4 of 0.7 is given by this form. F, we have the fifth derivative of psi x 0.7 minus pi over 2 raised to the power of 5 over 5 factorial. Okay, and our psi is between 0.7 and pi over 2. Okay, so please recall our definition here, our theorem, not definition, theorem, Taylor's theorem. So replace n by 4 and use this one here. Okay, where psi is between x and x naught. Our x naught is 0.7. Okay, so letter C. And before I will proceed, I think I made a mistake somewhere here. I guess I was wrong in this one here, the value of this one, because I've noticed that in the Dismos graphing calculator, I use the region mode. Okay, I use region mode here, so that's why the answer is 0.69 before. Okay, 0.69. So the we should use using your calculator, you will use the degree mode. Okay, please remember that. Okay, so use degree mode. The answer for h of 0.7 is this one, 0.2490 2490 24904 2490. You should run off to, let's say, 5 decimal place. Here 0 point, I made a mistake here. This should be negative 0.24905. Okay, let's round off to 4 decimal place. Okay, since we are using 4 decimal place here, that one. Okay, so my right 2490. So this will become this one here, 0.2490. And since this is p sub 4, we are correct here. This is 2278. So I guess we also have a mistake here. This should be 2490 plus, okay, 2490 0.2490, this one here, 2490 2278. So the answer is 0.0212 0212 0.212. Okay, I guess that's the correct one. So let's proceed. Okay, by the way, the value for this expression here, this one, the value of this one, if you use if we will use our this most scientific calculator, this is equal to this one, 0.7 minus pi over 2 over 120. This one raised to the power of 5 over 120. So the answer is negative 0.00417. Okay, so but anyway, this is negative, this is, let's try another color here, negative 0.00417. okay, so 5 factorial is 120. Okay, so let's proceed. Okay, since we have a uh, the fifth derivative here, so let's compute this first. Okay, this one. Okay, so we need to differentiate f one more time. One more time. Okay, so f, not f but h, sorry, this is h, sorry, we have h, and also I'm so sorry here, this should be h, this should be h. Okay, did I make a mistake here somewhere? Okay, that's correct. So our fourth derivative is this one, x sine x minus 4 cosine x, x sine x minus 4 cosine x. So x sine x, so let's get the derivative. X sine x, so x derivative of sine is cosine, plus sine x derivative of x is 1, plus that's 4 derivative of cosine, am I right? It's minus 4 cosine, derivative of cosine is negative sine. Okay, so we have, let's move back a little. Okay, so minus 4 derivative of cosine is negative sine x. Okay, so this is, if we are going to simplify, this is x cosine x plus 5 sine x. Okay, so this is our fifth derivative. Okay, so what we will do here, okay, so we will have to find an upper bound, okay, for this one. Since our psi is between 0.7 and pi over 2, we can find an upper bound for h, the fifth derivative of x, and thus an upper bound for r sub 4 of 0.7. Okay, using triangle inequality, this is in calculus, no, not calculus, in real analysis, so, or in your fundamentals of mathematics, it's a very obvious inequality. So we have to get a bound here, so since we are going to use this one, okay, this equation, so by triangle inequality, r sub 4 of 0.7 absolute value, which is equal to the fifth derivative of psi times 0.8 minus pi over 2 to the 5 over 5 factorial. This will become, notice that our fifth derivative is this one. Okay, so replace x by psi, so we have psi of cosine psi plus 5 sine psi. We can move this one, we can apply the property of absolute value. Absolute value of AB is equal to absolute value of A times the absolute value of B. So we can move this one outside, and then as we know before, as I write it here, I've said that this is equal to negative 0.00417. So taking the absolute value, so we have a positive 0.0417. So 0.0417. Okay, and then using the triangle inequality, this will become 5 times 0.00417 absolute value of sine psi plus 0.00417 absolute value of psi times absolute value of cosine psi. Okay, so okay, from this equation to this one, you use the triangle inequality. If you recall, we have absolute value of A plus B is less than or equal to absolute value of A plus absolute value of B. So this is what we call triangle inequality. So our A is here, this is our A, and this is our B, and then distribute. Okay, so after this, let's find an upper bound for sine and cosine and psi. Okay, so note that on the interval 0.7 pi over 2, our sine psi is a positive increasing function. Why is that? Increasing function. And because of this, absolute value of psi can be bound by 1. Okay, let's try to analyze it using a graph. As you have noticed here, let's try this one. Let's graph sine x. Okay, so this is the graph of sine x. Let's replace this by color orange. Okay, and then let's zoom out. Okay, notice from as I've said, in the interval 0.7 to pi over 2, let's try plotting 0.7 because we label it as x since it is a value in the x-axis. and x is pi over 2, so we have this one here. So the green one is 0.7 and the purple one is this one here, vertical line. Okay, as you have noticed, in this interval, let's zoom again, from 0.7 point here up to here, notice that our sine function, the orange one, is this one here. Okay, and in this interval from 0.7 to pi over 2 or 1.57, our function is increasing. Okay, so positive increasing function. So the maximum value that it can get from 0.7 to pi over 2 is 1 here, this one here. Okay, this one here. So that's the reason that we can bound sine psi to 1. Okay, sorry, let's move it somewhere here. Okay, and sine of psi is equal to sine pi over 2, which is equal to 1. Okay, for the second term, here, we have to find an upper bound for psi and cosine. Okay, for the second term, let's move in this side somewhere here. Okay, for the second term, we can find an upper bound by observing that absolute value of sine of psi attains a maximum value of pi over 2 on the interval 0.7, sorry, this interval 0.7 and pi over 2. Okay, so that's very obvious. So we can have a function y is equal to psi or y is equal to x, and then as you have noticed here, in this interval from 0.7 to 1.5, so y is equal to psi or x attains a maximum value here. So if we write y is equal to x, that one, so the what we call this one, the highest value is this one here, pi over 2. So replace your x by psi. Okay, so because we cannot graph psi here, it is a default variable in the Dismos graphing calculator that we have to use x. So the highest value is this one. Okay, psi. Okay, this one here, substitute. So this is 1.2 0.57. Okay, so and how about cosine? And cosine psi, which is, if you try to graph, it is a decreasing function, decreasing function, decreasing positive function. So decreasing positive function, on 0.7 in this interval, pi over 2. It has a maximum value of cosine 0.7, which is equal to, again, if we are going to use our graphing calculator, let's say this one here, let's delete that one, let's try cosine. Okay, let's try cosine x, that one. In the interval, this is decreasing from 0.7, this one here, up to 1.57 or pi over 2. So this is a positive decreasing function, okay, in the interval 0.7 to pi over 2. So that's the reason that the highest is this one. It will attain its maximum value at this point. Okay, cosine of 0.7, and cosine of 0.7 is 0.7 is 0.7648, 0.7648, 0.7648. Okay, so putting this together, we get this one, r sub 4 of 0.7. So as you have noticed, let's look at here. First that one. Okay, this one, this area here, so sine pi is, we can replace it by 1. This one here, we can replace by 1. We can replace by pi over 2, and we can replace by 0.7648. Okay, so 500. Okay, this is first that one. 0.00417. Our sine is 1 plus 0.00417, and then we replace absolute value of psi by pi over 2, and our absolute value of cosine psi is replaced by 0.7648, and this is approximately equal to let's have our calculator. We have 5 times 0.00417 times 1 plus 0.00417 times pi over 2 times 0.7648. So our answer is 0.02586. So this is approximately 0.02586. Okay, so what does it mean? Therefore, we have our estimate for the actual error, which is where's that one? Let's finish this one first, which is blank from part B is 0.02586. That's the end of the solution. Let's go back to part B. Where are you? This one, 0.0212. 0.0212. Let's circle this one. 0212. 0212. Okay, so that's how you are going to solve example 8. So for our next lecture, we will be discussing here. We will be discussing we will be discussing before we go to our problem set, we will be discussing Python basics next topic, and computer arithmetic before we go to chapter 2. So before I end, this is your problem set, so you can answer this in yellow paper or blank paper, and then take a picture and upload it in our Google Classroom later, after I will make a portion in the classroom on how to upload your first problem set. Okay, so please wait for our next lecture. Thank you so much for listening. God bless everyone. Okay, escape.